In this presentation, we will introduce the basic idea of sampling distribution of sample statistics. The sample statistics considered here are sample mean and sample proportion. An important statistical theorem, the central limit theorem, is also introduced. We have discussed this flowchart in previous presentations. To better understand the population parameters, we will need to draw independent and representative samples from the population. Sample statistics can be calculated for each sample. When we draw different samples from the population, the sample statistics, say sample means, from different samples could be different. This is because the sampling procedure is a random process and the samples are different from each other. In this presentation, we will discuss the sampling distribution of the sample statistics. The definition of the sampling distribution is the following. A sampling distribution of a statistic describes the distribution of all possible values of a statistic over all possible random samples of a specific size that can be taken from a population. Let's break the definition into several important ideas. First, we sample repeatedly from the same population a few times, because each time the samples we draw from the population are likely to be different from previous draws. The values of a sample statistics from different samples are likely to be different from each other as well. You can think of the sample statistic here being a sample average, or sample mean. The sample mean GPA of 30 students is likely to be different from the sample mean GPA of another 30 students. Second, later in this video, we would discuss the sample statistics typically depend on the sample size. To make a reasonable comparison of the sample statistics from different samples, we would have to fix the sample sizes to be the same. That means we don't want to compare the sample average GPA of 30 students with the sample average GPA of 300 students. Lastly, the sampling distribution of a statistic is the random distribution of the sample statistic we're interested in. That means we would like to understand how the sample average GPA of 30 students spread out in general. Let's first think about the number of different samples of a fixed sample size that can be taken from a population. Say the student population is a total of 180 students, and we want to draw samples of size 30 from these 180 students. The total number of different ways of drawing 30 from 180 can be calculated using this combination notation. There are so many different ways of drawing 30 from 180. This shows that there are almost uncountable number of different samples of size 30 from a population of size 180. Therefore, it is almost impossible to draw all different samples of size 30 students from the population and compute a sample average each time, and then use a histogram or other techniques to summarize the distribution of the sample averages. This is simply because there are just too many different samples of size 30 out there. We are grateful that there is an important statistical theorem that is able to generalize the distribution of the sample average for us, so we don't have to draw samples repeatedly and examine at the sample average one by one. From previous presentations, we have already discussed the normal distributions can be fully determined by its mean and its standard deviation. This is that if both the mean and the standard deviation of a normal distribution are given, we know exactly which specific normal distribution that is. Central limit theorem, also known as CLT, is an extremely important theorem in statistics. It has a wide range of applications to many statistical problems. We will focus on its application for the sample mean and the sample proportion in this video. There are two parts to this theorem when applied to the sample mean. First, if we know the population is normal with mean mu and standard deviation sigma, sample means would also follow a normal distribution with mean mu and standard deviation sigma divided by square root of sample size. The second part of the theorem is that if the distribution is not normal, or we are uncertain whether it is normal or not, with a mean mu and a standard deviation sigma, and the sample size is at least 30, the sample means would also follow a normal distribution with mean mu and standard deviation sigma divided by the square root of sample size. The two results are similar to each other, with the only difference being whether we have the information this population is normal or not. If the population is not normal, we would need the sample size to be at least 30 to have a normal distribution for the sample means. If the population is normal, sample means would be normal for any sample sizes, whether it's 2, 30, or 100. The standard deviation of a sampling distribution of a sample mean, such a long name, is typically called the standard error of mean. That is also the sigma over square root n part. Central limit theorem can also be applied to sample proportion. The theorem does not have any assumptions on the distribution of the population. It says that the sample proportions in general follow a normal distribution with mean population proportion P and a standard deviation of a square root of a population proportion multiplied by 1 minus population proportion divided by sample size. Again, the standard deviation of a sampling distribution of sample proportion is also known as the standard error of proportion. Central limit theorem's results have many important implications. First, the sample averages and sample proportions follow bell curves or normal distributions. Normal distributions are simple and convenient to analyze. Second, the center of these normal distributions of sample statistics is right at the population parameter, population mean or population proportion. Lastly, standard deviation of the normal distribution, also known as the standard error, depends on sample size, is inversely proportional to square root of n. As sample size increases, the standard error becomes smaller. Because standard error measures the spread or variability of the sample statistics, a large sample size is able to reduce the variability of the sample statistics. That is a desirable feature when we design an experiment. What we have not discussed in this presentation is that, as the sample size increases, the sampling distribution of a sample statistics becomes eventually closer and closer to a normal distribution, and that's why we require sample size n to be at least 30 for the sampling distribution of the sample means. Say the original observations, x's, all have a standard deviation of 10. When we take samples of a size 100 repeatedly, the sample averages of 100 x's do not have a standard deviation of 10 anymore. It is not surprising the sample averages of 100 x's have a smaller spread than that of the original x's. CLT tells us that the standard error of sample averages of 100 x's is actually sigma over square root of n, that is 10 divided by square root of 100, that is 10 divided by 10, and that is 1. We can see that averaging reduces the variability from 10 to 1. We summarize several notations we just discussed here. Standard deviations and standard errors are all measures of spread and variability of various items in a collection. Population standard deviation sigma is for population. Sample standard deviation S is for the sample. Standard error is for the sample mean or sample proportion. Sometimes sigma is not a given. We would have to approximate it using the sample information, which is the sample standard deviation S. If population proportion P is not a given, we would have to approximate it using the sample proportion P bar.